we go to the next proceedings. Today, we are honored to introduce Dr. Aamod Desai, Assistant Professor in the Department of Chemistry, Madras. Completed his integrated MS PhD from specializing in MOFs for emissions. Later worked as a postdoctoral researcher at the University of St. Andrews, focusing on energy storage. This research brings quantum chemistry and real-world solutions for the porous materials for energy and security. Storage and electronics. We will celebrate the 2025 Nobel Prize in Chemistry awarded to Richard Robson's, Omar M. Yagi, and Susumu Kitagawa, and explore the challenges and breakthrough ahead. Let us extend a warm welcome to Dr. Aamod with a round of applause. Over to you, sir.
Thank you. With this one. Just for 1 minute. His advisor worked with Susumu Kitagawa. We have to one step away from the. That's for YouTube. Okay. So, good morning, everyone. Thank you for having me over here to the entire organizing team of TNSF. And today I'll be talking about the adventures of these three gentlemen. And the adventures didn't happen yesterday, day before. They happened in the late 80s and the 90s. So this is going to be like a bit of a history tour. We go back 30 years down the line and see what these guys aimed or did and how this field has evolved over a period of time. Right? So these are the three gentlemen, as was said in the introduction, which is Richard Robson from Australia, Umar Yagi from the US, and Professor Susumu Kitagawa from Japan in Kyoto. So the title of my talk is Adventures of Nanospace Navigators. It is no short of an adventure for all of the three of them. And today I'll kind of demonstrate what essentially nanospace navigation is. And what the way I intend to do this is the way I intend to do this is introduce the topic of MOFs. I'm sure a lot of people are not very familiar with the term MOFs. So I'll just start with a brief introduction. How did they arrive? Essentially, that's the key thing to getting this Nobel Prize. So a bit about that. And then the key inventions of all of these three gentlemen. And then the stories about how they got inspired to do this research. And of course, the last two topics are a bit more personal account or in terms of how this field is going ahead. And essentially giving an idea about who all are working in the area of MOFs. So this is kind of the outline of my presentation, which will be roughly around 45 minutes or so. Right? So I'll start with this particular image. So this is an image that the nobelprize.org website promoted to sell this idea of what a metal organic framework is. So if you look at this image, what essentially it means is that you have your home, you welcome guests into your home, they have tea, coffee, food, and then they go out of their home. So essentially the part that kind of is a MOF is essentially that home or a place where people come in or guests come into it, and then the guests have spent some time and then they go away. So this is how MOFs can be seen or thought about when you're looking at it at a very simplistic level. And this is what nobelprize.org wanted to show with this particular image. Right? So in terms of more sort of chemistry intuition and seeing out how they look like, the name itself is quite intuitive, right? It's metal organic frameworks. So it has to have a metal component, it has to have an organic component, and it has to have like a framework arrangement or a framework like structure. So again, in a simplistic diagram, if you have an organic ligand that looks something like this, which is linear in nature, you have a metal ion or a cluster. Again, from very preliminary chemistry understanding, the metal ion essentially is directional. So the bonding has to be either 6 coordinate, 4 coordinate, whatever number of coordinates, but the direction kind of comes from the metal ion. So if you have a metal ion that is going to be octahedral in this particular example. It is going to connect to 6 different organic ligands. And of course, these syntheses are carried out in the presence of some guest molecules, which are typically solvents. You can think of water, methanol, ethanol, which are some of the common solvents. And these solvent molecules occupy this empty space. And this is kind of the like the small unit that forms. But this is not the only end of it. So this kind of goes periodically, and this extends into 1-dimensional, 2-dimensional, 3 dimensions. And this is your house that was I had shown in the previous slide. So this is how you construct your home, and this has got a lot of empty space inside it. So in case of real estate, this is quite a enriching property, right? The main advantages in terms of fundamental science is that these materials have got a lot of porosity. I'll explain what porosity is in a bit, but they've also got crystallinity. So crystallinity is something all of us associate. When we go to a jewelry shop, objects that shine or glitter, they're essentially crystalline in nature, right? So all of these materials tend to be very crystalline. And this is useful for not only chemistry, but also for material sciences and for particular applications when we have the ability to have something which is crystalline in nature. We also can tune the chemical and physical properties because we have got metal ions, we have got organic ligands, and we can change the physical properties, the chemical properties of each of these building units, and also change the properties of the eventual structure that forms. So this is kind of this holistic idea of what essentially a MOF is, or some of them like to call it as a porous coordination polymer. And why that is important, I'll get to it in a few slides. One of the key things about MOFs, if you want to understand it again, if you're not convinced by this argument, is if you look at the scaffolding arrangement, there's a lot of construction happening in Chennai and around us, right? So if you go around, if you see some kind of a scaffolding arrangement, you can think of this as a metal organic framework structure. The pillars that go straight or horizontally, those would be the organic ligands, and the corners at which they meet would be like a metal ion. And the corners would define the geometry by which the arrangement would be. So instead of having a square grid, a 4 connection, if you have a 6 connection, you'll get an octahedral or a 6 sided geometry. So essentially, a scaffolding arrangement is one which kind of explains what a MOF is on a very larger scale. Right. The second thing about MOFs, or which is very special about MOFs compared to other materials, is again, you can choose any metal ion in the periodic table. You can choose any organic ligand that you can think of or make in the lab, and you can combine those two and make any kind of structure. So for those who have played with Lego-like materials in their childhood, it is something which resembles that. You choose any building block, you mix it with anything else, and you can form an architecture that looks symmetric. So essentially, in terms of the overall architecture, it looks something like a scaffolding. But to construct that scaffolding, you need some building blocks. And those building blocks can come from a Lego-like arrangement, which is very simplistic view of how a MOF is formed. Right? So to understand the idea of porosity, I'll spend a few seconds over here. All of us know a football stadium. Right? Anyone knows the size of a football stadium? Can suggest some surface area. What is the area of this football stadium in terms of numbers? Any
100 meters by 50 meters.
Right. So if you can calculate the total area for a professional football field, it is something around the region of 7,000 meters square. To put everything into the context why MOFs are so special is that all of that surface area can be combined into 1 gram of material. So this particular MOF, which is an example of DUT60, don't have to worry about the name, but this particular MOF has a pore surface area of 7,800 meters square in 1 gram of the material. So if you take 1 gram of this particular material, you're actually getting surface area, which is equivalent to an entire football stadium, which is kind of the beauty of these materials. So the surface area that I'm talking about is just the internal pore surface area. I'm not talking about the material surface area. It's not going to be that big a material, but it's just the internal surface area that's so special. And again, for those who want to correlate what 1 gram means, essentially when we go out for tea or coffee, we get a sugar sachet, and this sugar sachet is roughly 5 grams. So 1 gram would be 1/5 of this sugar sachet, and that has a surface area of 7,800 meters square, which is kind of this putting everything into context and why these materials are so very special. Right. The second thing about them is how do they construct it in terms of chemistry? All of us have done some basic chemistry in our some level of education, where we start looking at connection between a metal ion and an organic ligand. But the standard textbook definition is that we connect metal ion and organic ligand, and that's it. We end it there. But what these three guys thought is instead of connecting it at R, if we have another symmetric unit that connects to the other side of the R, and can we connect the same metal unit to the other side? Essentially, what we do is form like a network. So instead of this double oxygen groups over here, if you have another carboxylate group attached to the R side, we can start forming a two-dimensional layer. And likewise, instead of putting L as one unit, if we can connect the L in the third axis, essentially we are forming a network structure that goes in all the three directions and which encapsulates this porosity. So this is what something it looks like. So the blue atoms in this one is the pillars that form this vertical layer. The green units, you don't have to worry about the what organic ligand that is, but essentially this particular rod, that is the organic ligand, that goes in the two dimension. And then the two dimensional is now connected by this third axis. So essentially this forms a three-dimensional porous structure. And this is what would be called as a metal organic framework, right? In terms of applications, they've been used for a lot of things. They've been used for gas storage, gas separation. They've been used for energy applications. They've been used for catalysis, even for ion conduction and things like that. So in terms of application, there is no shortage of where all of these materials can be used at. So just to put these numbers into context, I'll just provide a few statistics. So at the moment in the literature, uh, there are more than 1 lakh of these materials known, and there is no limit to it. Essentially, we can combine any organic part, any metal salt, metal ion, and then we can form a metal organic framework. But at the moment, there are more than 1 lakh crystal structures known that are well characterized and known in the literature. In terms of density, the density of water is 1 gram per centimeter cube. But this material is so light that the lowest known density is 0.1 gram per centimeter cube. So it's again something like a cotton-like material, which is very light and fluffy, but which has got a lot of internal surface area. And again, if you're a science enthusiast, as you are, essentially the number of papers that are coming out in this field has exploded in the last few years. So these guys worked, or the people who won the Nobel Prize, they worked in the 80s and the 90s. And at that time, there was hardly any interest. You can see in the number of publications in that year. But in the last 10, 15 years, this has just exploded. And we are now getting more than 10,000 papers every year in this particular field. So this is kind of showing the interest that is happening in this area globally, not just in one particular country or region, right? So before I go into my next slides, I just wanted to put some context into what organic ligands essentially are part of a structure. So I told you at the beginning that the metal ion gives the direction, but the organic ligand is equally important, because if the organic ligand doesn't have the symmetry, the structure is not going to form a symmetrical structure, because we want periodicity over a long range. To form something which is periodic over a long range, we need to have symmetric building units. So you don't have to worry about the internal components of this. But essentially, if you look at these molecules, all of them look pretty similar, don't they? Because in the case of the first one, there are 4 carboxylate groups that are at particular angles. In the case of maybe the one which has got nitrogen atoms, it has again got 180 degrees of binding modes. So again, the idea that the binding has to happen in a symmetric fashion. And to carry out that binding in a symmetric fashion, you need symmetric building units. So we have got 2 components. One of them gives the direction, which is the metal ion. And the second part is the organic ligand, which essentially gives the direction and continues to propagate in all the 3 dimensions. So the building unit is very, very important. And you don't need like very exotic or very long building units. You can also have small building units like some of these examples that are shown over here. In terms of synthesis, you might think that they need complicated synthesis. Actually, they don't need any complicated synthesis. You can even cook these materials in a microwave oven, not the one that we have in the kitchens, but slightly modified ones. You can actually use basic heating elements to prepare these materials. You combine the metal ions, you combine the organic ligand, and you essentially form a self-assembled structure. So the beauty of these materials lies in the design, not necessarily in the how they're synthesized. This is kind of the thing to highlight over here, that if you choose right building blocks, you can construct a metal organic framework that has got porosity, that has got periodicity, that has got perfectly framework-like structure, but you don't need to worry about your synthesis method. You can just prepare it by some forces, and that should be enough. So this is just to highlight that it is pretty easy to make these materials, right? So with this, I will now go into a bit more details about why these guys won the Nobel Prize. And on this slide, I won't talk about that, but what I'll try to highlight over here is the key publications that won them the Nobel Prize. So for example, Professor Robson's group, they published this paper in 1989, which is why they won this Nobel Prize. The second one was from Omar Yagi. He published this paper, or his group published this paper in 1995, and Kitagawa's group published this paper in 1997. So all of their individual contributions were published way back in time. And again, this is kind of to show that that the research that we do today necessarily does not have to win a Nobel Prize tomorrow. It can take 20, 30 years down the line. You have to be alive though, because to get a Nobel Prize, you have to be alive to win the Nobel Prize. So that is one thing. But just to highlight that all of these people did their research way back in time. And today I'll try and convince you that their story is very, very inspiring and something that we all can learn something out of it. But as a young researcher in this area, how I see the contributions from all of the three is slightly different. So in terms of the basic research that they did, how I see it is that Robson suggested that you can create pores. So he suggested you can construct these molecules and have cavities inside them. What Yagi did is he said that you can stabilize these materials. So you can think of it that these materials have now got a lot of empty space. They've got very low densities. So essentially, you're not going to have stable structures out of them. So the way to stabilize them is something what Yagi's group did. And what Kitagawa did is he suggested that we can actually use those pores. Those pores don't have to sit there idle, or we are not making these materials just for the sake of it. We actually want to utilize them. So what his group did is they tried to put some gas molecules into the structure and get those gas molecules out of those structures. And then you use it for things like catalysis, gas separation, and other things. So this is how I see these three the contributions from these three people working in three different directions, but having MOFs at the central theme. Right. So with this, I will go to the story of how did MOFs arrive. So it's now going back into time. It's like kind of going back into history and understanding what kind of were the steps or the key milestones that led to the discovery of MOFs. So it doesn't start in the 1980s or 1990s, but it actually goes way back in the 1800s. So Alfred Werner, who is known as the father of coordination chemistry, he kind of discovered these kind of materials. And what essentially he said that if you have a metal ion, if you have some kind of donor groups, or in this case, ammonia and chloride, you essentially have them binding in a very specific geometry. You cannot have them binding randomly. So depending upon the coordination ability of cobalt, all of these groups will bind in a specific manner. So this is kind of, again, like one of the building blocks or the heart of where this kind of field has evolved. And in the Nobel citation, of course, he won the Nobel Prize in 1913, but in the Nobel citation for the current year, his contribution has been marked specially. So they said that what his contribution did is predict joinery method in structural design. So until then, there was kind of just this random assumption that we are able to make these materials, but there was no kind of direction or the way this can propagate. But in his work, what it was suggested that if you have a cobalt ion, it will have 6 coordination number, and 6 ions can bind at a very specific position. They cannot bind very randomly. So his contribution is really important in that sense. The second contribution is the discovery of Prussian blue. So a lot of you might have seen some dyes and pigments and everything. Tamil Nadu is famous for having dye industries, but Prussian blue is one of the original dyes that was discovered in the 18th century. And it has got this very simple structure. It has got iron, it has got a carbon, and it has got a nitrogen. That's it, 3 different elements. And they are kind of arranged in this periodic manner. But until 1936, no one knew the structure because X-rays were not discovered, X-ray machines were not available. So until 1936, people just had this idea that there is iron and carbon and nitrogen, but they didn't know how it was bound or what the structure looked like. But in 1936, in this particular example, they found that the structure is actually looks like a MOF structure, right? It has got periodic arrangement, it has got a well-defined geometry around the metal center, and it just connects in 3 dimensions. But the more important thing, it has got some empty space in between it. So it has got some cavities that can be accessible to guest molecules. So Prussian blue's invention is also marked as an important discovery in the Nobel citation for this year. And what it says that in principle, it would be possible to design and produce such cavity forming structures and to control the inclusion of small molecules inside them. So again, Prussian blue, which was known in the 18th century, the structure was known in 1936, is again a foundation step for where MOFs came about. Right? In fact, the term coordination polymers, I refer to it as MOF or a porous coordination polymer. The term coordination polymer actually finds its roots in 1916. So there was a publication from a group in Japan where they showed that they made a structure and they predicted it to be a coordination polymer. So the term coordination polymer again is more than 100 years old. It's not a new term. But more importantly, the key steps that happened in this area was in the 1950s and 1960s. So this publication in 1959, again from a group in Japan, is that just took a simple organic molecule, treated it with copper nitrate, and formed this structure, which has got, again, periodic arrangement, well-defined symmetry, everything. But again, more importantly, it's got some empty space in between. They didn't understand or realize that this empty space was actually really important. They just made this structure, reported it, that's it. So again, their group is really, really important in the discovery of MOFs. The second example is actually from a group in USA, but the authors are from Indian origin. I think they're from Tamil Nadu itself. I don't know the roots, but they're actually from Indian origin. And they went to the US and reported this example. So that instead of taking this organic molecule, they took thiourea, they reacted it with copper nitrate, and they formed this particular structure. But a key thing in that publication is in this particular paragraph. What they said is you don't have to worry about the first part, but the last sentence. They said that the function of the nitrate groups, which is part of the building unit, apart from some hydrogen bonding, is to fill the holes that are left in the polymer. So again, this idea or this intuition that there is some empty space that can be created essentially is discovered in or was suggested in the 1960s itself, which is quite amazing for the development of this field. But for the next 20, 30 years, nothing happened. No one came up with this idea or found that this is interesting enough. So until the time when Richard Robson, Yagi, and Kitagawa, they came into the field, this field was lying a bit low, right? So then all of these three people entered this area, found that this can be useful, and then they started working in this area. So the next segment of my presentation is actually going to be talking about their specific discoveries and the stories that actually led to the key discoveries. And I'll start with Professor Robson's group, which is based in Australia. So this is the photo that was taken right after the Nobel Prize announcement, I think a day or two later. And this is how he looks like now. He's quite old, he's retired, he just goes to the university to meet his colleagues and students, but he doesn't work anymore as a professional. But this is an example of him in his office, essentially. So what he did, or the key publication that led to the Nobel Prize, is this paper in 1989. So his idea was that if you take a symmetric organic ligand, which has got four connections, the one in the circle at the corner, and if you can connect that organic ligand with copper ions, which is in this purple circles, and you can just try and think of it connecting in multiple dimensions. So you have a tetrahedral geometry, you connect it with another tetrahedral unit, and then it can just keep on going in 1, 2, and 3 dimensions. And what he suggested, or the first sentence of his publication was, we propose a new and potentially extensive class of solid-state polymeric materials. So look at the vision of that man, that in his publication in the first line, he thinks that what he has created is going to lead to the generation of materials or a class of materials that was not there in the literature before. So that is the first sentence of his publication. The second paragraph of his publication is actually that something that actually underlines the idea of MOFs. He said that the very striking feature of these materials is the large size of cavities that are produced, even by rods that are very small in length. So if you have an organic ligand that looks just one phenyl unit or one benzene unit, you can still create cavities that have got much more empty space than you can think of. So normally what we think of is if you have to create a lot of empty space, you can just look around yourself. We need to create a tall building. It has to have long pillars and everything. But what he suggested, you can design the molecules in a smart way that you can just take a small unit and you still have a lot of empty space in between them. And this is what he kind of suggested in his publication. That is kind of the thing that won him the Nobel Prize. But his story is slightly different. And I think a lot of times we are told by our teachers, by our mentors, that we should teach. We should teach the younger generation. Even if we are learning, we should teach our colleagues and peers. And why teaching is so important is in his story. So he joined University of Melbourne, and about 8 years into his teaching time, the head of the department, he said that the teaching models are not good enough. We need to change the models or the way we teach our students. So he gave him a task, go to the workshop, create new models to teach students how atomic bonding works. So he went to the workshop, he created these wooden models, and then he started connecting them in his office one day while he was preparing his lecture notes. So he came up with this idea that he's teaching atomic bonding. He's taking one atom, he's taking another atom, he's trying to connect those two atoms. But he thought, like, instead of connecting atoms, what if he connects molecules? So this is one molecule, this is another molecule. What happens if you try and connect those molecules? And can you make something bigger out of it? This is kind of his inspiration. And this came from this very basic idea of preparing atomic models for teaching material. So what he did essentially, it took him 10 years. So he used to work with these models, go to his class, come back from the class, and then really think about it after that. Because we have, as faculty members, we have got a lot of other things to do, right? But when he kind of put this into practice. He called a student one day, about 10 years later, in 1985 or so. He called a student and he said, like, okay, let's put this into practice and do an experiment and try and make these materials. And 4 years later, he came up with this publication where they actually made this framework material, which is now the origin of metal organic frameworks. So a very simplistic idea of how teaching can trigger some thoughts in your head can lead to even a Nobel Prize. This is his story. The second story is from Umar Yagi, who is from USA. Uh, Essentially, what he did, as I said at the beginning, is he stabilized the structures. So the structure that Robson proposed would collapse. So the moment you synthesize the material, you try and remove the guest molecules of the structure, the bonds that form the metal organic frameworks are weak. So the structure would collapse itself. So it's like a house that doesn't have good concreting. So the house completely collapses. Or it's like this cards that we play at in our younger days, where we try to build houses from the cards which don't have any joinery connections. So the moment we kind of blow some wind, it just collapses altogether. So Robson structures was something like that. But what Yagi did is Yagi said, if I change the organic ligand and I use carboxylic acid, carboxylic acids are known to have strong bonding with metal ions. So he chose a carboxylic acid, again, very symmetric organic ligand. He connected it with a metal ion and he formed this beautiful structure which had got some empty space. So the G circled over here is this empty space. I purposefully took this image from his original publication just to illustrate this idea that at that time, the quality of images were not great. But what these guys did is they had the vision to propose what they were seeing. So he thought that he's getting some empty space, he's getting a periodic structure, but he kind of made this structure in this particular figure. The second contribution, what he did is few years later. So the original publication is in 1995. The second publication is in 1999. So in 1999, instead of choosing a complicated ligand, he just chose a smaller ligand and he created this beautiful structure, which is MOF5. So in this image, which has got this black background, it's actually showing just a cross section of it. So this is a three-dimensional structure which runs in the 2 dimensions in this image and also in the third dimension, which goes inside the screen. So this is a three-dimensional structure. But more importantly, when he measured the surface area, he found that this particular material has got 2,900 meters square in 1 gram of the material. So the original example that I showed of the football stadium and things like that, these guys already started getting there, because in this example they got halfway there, which is about 2,900 meters square per gram. And despite having that much porosity, this structure was completely stable. So the moment you took out the gas molecules, which is in these yellow balls, the structure was not collapsing. So now we have a house that is stable enough to insert gas molecules, to remove gas molecules as well. So this was one successful experiment that Yagi's group did. In terms of chemistry, he's not known only for this. He's known for a few other things. For those who might be interested in reading more, this is something which is an auxiliary of what MOF research happens. So you start with the structure, the one on the left, which is this MOF5 structure. So what happens if you change the length of the organic ligand? Does the bonding change? Do the properties change? Essentially, that doesn't happen, because now you still have the symmetry of the organic ligand and the binding groups. So if you go from the left to the right, you are essentially just changing the cavity size. You're not changing the structure. So again, the symmetry of the building blocks is so important. And this is what he coined the term as isoreticular MOFs. So isoreticular essentially means if you have the building units in some geometrical symmetry, they can form the same structures, and the only thing that changes is the porosity. The second contribution that a lot of people are thinking that he might win a Nobel Prize for this as well is essentially to remove the metal ions. So what happens if you just take away the metal ions, but use the building units, just organic building units, and have them very symmetric in manner? So a very common reaction that is known in organic chemistry is if you take boronic acid, you combine boronic acid units together to get this anhydride in this particular reaction. So instead of taking just one side of the boronic acid, what happens if you take boronic acid, which is again para position or 180 degrees opposite to each other? You end up getting like these kind of structure, which are again long range materials that have got some porosity inside them, which is up to 15 angstrom in this particular structure. So he has created this field of COFs, which is covalent organic frameworks that don't have a metal ion, that are based purely on organic materials, which have got symmetric building units. So this is something to watch out for. So in a few years' time, if COFs win the Nobel Prize, don't be surprised if Umar Yagi is once again at the forefront of it. The story for Umar Yagi, though, is slightly different. He wasn't born in a privileged country or a privileged location. He was born in Jordan. And at the younger age, his house didn't have running water, they didn't have electricity. And he was like in a very poor family. The only place that he got inspiration or encounter with chemistry was in the school library. So he once went to the school library, he looked at organic structures. He just got inspired by it. He didn't know or understand what was there. But his father kind of pushed him to go to the US. So at the age of 15, he moved to the US. He didn't know English much at all. He couldn't understand or speak English, but he just went to the US and then picked up English there and studied at New York. But for those who are into academic research, one of the other fascinating stories about him is that when he started his independent career, uh, the only goal that he had at that time that he should publish one paper which gets 100 citations. And now his research group has over 2.5 lakh citations as of now. And it will definitely keep growing because he's now a Nobel laureate. So a lot of people will cite his work. But this is kind of how it started. He started his journey in 1992 with a dream of having one publication of with 100 citations. And now he's got more than 2.5 lakhs. So dreams can be big and dreams don't have to, you shouldn't be limiting yourself with dreams. That's the gist of his story. The third hero of our presentation today is Susumu Kitagawa. He's based in Kyoto in Japan. A very soft-spoken person. I had the good fortune of meeting him a few times because my PhD supervisor worked with him. So he's a very humble, down-to-earth person, and he would be very welcoming you. And if you go have some questions, some technical questions, he's very easy to approach as a person. But his key research area, which is what I want to highlight today, is essentially how do we utilize these pores. So Robson suggested we can create pores. Yagi suggested we can stabilize those pores. But Kitagawa is the one who actually said that we can use these pores. And it happened so because Susumu Kitagawa is not an inorganic chemist by training. He's a physical chemist. So physical chemists want to use these materials for some applications. Inorganic chemists are more interested in how these materials are made and how these materials are stabilized. So the first two heroes of the talk were inorganic chemists. So they were more interested in the structures, but Kitagawa is more of a physical chemist. So he saw this as an opportunity. He saw that there are empty spaces in these structures, and we can fill these empty spaces with some gas molecules or gas molecules, which can be of some practical importance. So what he did in this particular example, which has, again, we're not going into the technical part of it, but what is the thing to highlight is this yellow channel. So what he did is he just took oxygen, pure oxygen, he took pure nitrogen, he took pure argon, and they just threw those gas molecules inside these structures. And what he saw is in this adsorption experiment, where by increasing the pressure, you can actually incorporate a lot of gas molecules inside these structures, and you can even take them out. So you can think of this as a gas cylinder, which you have at home, which is an LPG cylinder, or a cylinder that you see around you in hospitals or something, which has got gas molecules loaded into a cylinder. So these particular materials can essentially be functioning like a cylinder. And some of the applications that I'll show in a few slides are actually doing that. So they're using these materials, they're pumping in gas molecules inside these structures and then releasing them in a controlled manner. So this is kind of the origin or the person who kind of thought of this particular idea, which is Susumu Kitagawa. The other thing that is kind of given attributed to him or his success is this idea of flexible MOFs. So all the structures that I've shown you so far are these rigid buildings that are in this, right? So they're not moving, they're not shaken by wind, but heat, rain, anything. But what he suggested is, can we have structures that respond to something? And I think all of us are embodying it. We have got DNA, we have got soft matter inside us. Anything that triggers us, like if we start getting pain, our skin swells. So essentially it's responding to something and the structure is changing. So it is a soft material. So what he thought like is, can we make MOFs into a soft material? And can we choose the building units in such a way that they're flexible in nature? And the way he thought about it is that if we remove the gas molecules, the structure changes to some other form. And the moment we put the gas molecules back inside, the structure goes back to its original form, which is in this square grid thing. So he's done a lot of work over the years. He didn't win the Nobel Prize for this, but this is one of the key contributions that he has done to this particular field. And he has done a lot of writing about it. He writes a lot of textbooks and reviews about it. This is a textbook that he wrote last year. Again, I had the good fortune of contributing a chapter to this. So me and my supervisor are one of the authors in one of these chapters. But the entire book is a very good reference resource for anyone looking to understand how flexible MOFs work. The other thing that he did is actually formalize this idea of classifying. We all have 1G phones, 2G phones, 3G phones. Kiragawa essentially used the same idea. He said that the first 1G morph is essentially a structure that if you remove the guest molecule, it collapses entirely. The 1G morph would be a Robson structure, which entirely collapses as soon as the guest molecules are lost. The second G or the second generation of morphs is Yagi's morphs, which when the guest molecule goes, the structure remains intact. It's a robust structure. The moment the guest molecule comes back in, just fill the empty space, but nothing happens to the structure. The third generation morph is Kitagawa's morphs, where he says that if you remove the guest molecules, the structure changes or changes some form of it. But the moment you put the guest molecules back inside it, it goes back to its original shape. So this is the three generations of morphs which he has classified. But his story is slightly different. He was, of course, an academic before he started working on this. But what is something that drives him, or what is something that he kind of likes, is this idea of usefulness of useless. And what he said is that when he started working on this area, no one believed in. They said, like, this is useless materials. You're just creating some materials and you're showing that these materials can uptake gas molecules. These are completely useless. So we wouldn't trust this. So he kind of kept patiently working on them. And he says that creation of uselessness, which is porosity or emptiness, is actually useful. And this is the philosophy that he really, really believes in. And to prove this, what he said is that when he wrote a lot of grant applications, a lot of publications in the 1990s, a lot of them got rejected. And the key thing that he kept getting is that these materials are unstable. We cannot believe these materials will ever be used in the market or be commercialized at all. So this is one negative feedback that he kept getting. But the other thing that he kind of believes a lot is in teamwork. So my PhD supervisor keeps mentioning that there are posters in their laboratories which constantly remind people that this is a team effort. It's no longer an individual effort, because all of us have got different brains. We have got different ways of thinking. So all of us have to combine together to solve a big problem. So teamwork is one big thing. And for especially those who are interested in chemistry or those who are chemistry enthusiasts, there is a very fun way of looking at it. So someone in 2009 interviewed him and they asked him, why do you like chemistry, or why are you a chemist? And he said, as a chemist, I understand the difference between ethanol and methanol. He's got his taste for wines and everything, but this is one statement that he made, that a chemist would understand what is ethanol and what is methanol and which one to drink and which one not to drink. So this is something that he he kind of mentioned in one of his interviews. Right. So the next part of my presentation is actually talking a bit about where this field is headed to, not specifically about their contributions, but in general about how this field has evolved and where it's heading next. Before I actually show some of these applications, I wanted to highlight two more examples where this field has actually exponentially grown. So the first example actually came in 2008 from a group in Norway. And what they did essentially, until that point, all the MOF structures that were known, even if they were robust structures, they were very moisture sensitive. So the moment you put the structure in high humidity, let's say put it in Chennai weather, they would start collapsing because the water molecules uh, bind well to the metal ions that disrupt the structure and they collapse it. But in this particular example, what they showed, if you choose a specific metal ion, which is zirconium in the periodic table, the structures that form out of this unit are actually very stable. They are even stable to different pH conditions. They're even stable to thermal changes. So they can be stable up to even 300 or 400 degrees Celsius. So this has been regarded as one of the key milestones in the development of MOFs. And what they showed is this idea of reticular chemistry, which I showed in a few slides before, that if you change the ligand units, if you go from 1-phenyl to 2-phenyl to 3-phenyl, you're essentially still getting the same topology, but the porosity keeps increasing and you're not getting any different structures. If you have the same geometry of the building units, you can end up getting the same self-assembled structure. So again, the idea of reticularity was demonstrated in this, but the most important takeaway from this example was the stability of MOFs by choosing the right building unit. The second example, which is essentially from a paper that came earlier this year, but what they did is essentially the very first slide that I showed had an octahedral metal center, which had got 6 coordination numbers. But what happens if you change an octahedral site to a tetrahedral site, or even 8 coordinated, 10 coordinated, whatever number of coordination sites you have? So on one of these axes, in this blue axis, they've got one metal ion. In the second axis, which is saying connectivity 2, you have got the second metal ion. If you combine these two metal ions, what are the typical nets that you can form? So it's like textile weaving, right? You just kind of form different patterns, and in your sweaters or in your clothing, you can form different patterns. And the way to form these different patterns can actually stem from the idea of the metal ions. So depending upon the geometry of the metal ions, you can actually form all kinds of nets. Of course, some of them are more popular. So for example, if you have got one metal ion which has got a coordination of 4, the second metal ion which has got a coordination of 4, that is the most popular one, which has got more than 400 nets that are known in the literature. And all of this has been analyzed from the 1 lakh crystal structures that are already known in the scientific literature. So this is this idea based on the metal ions, but you don't have just metal ions, right? It's a metal organic framework. So you can also choose the organic part. So instead of having an organic ligand which is two coordinate, if you have it 3 coordinate, you have 4 coordinate, 5 coordinate, 6 coordinate. 5 coordinate might be a problem in terms of symmetry, but 2, 4, 6, all of those are perfectly fine to form a long range framework materials. So if you can combine all of them, you get infinite possibilities. And this is kind of this idea that now the field has matured so much that if you start with a building unit, you know the geometries of the metal ion, you know the binding angles of the organic ligand, you can actually predict the net that it might form, which is something that wasn't the possibility 20 years back, where people were just trying to create structures. But now this field has matured so much that we can actually predict it based on all of this information and intuition. The second example that I wanted to highlight in as a key contribution is a lot of the times when we work in academic labs or in our undergraduate courses, we end up doing experiments that seem useless or not a lot of people appreciate why we are doing it. So this group in the Belfast in Northern Ireland, they essentially were working on scaling up MOFs. So they had this idea that if you take a metal ion, we take an organic ligand, and we just do essentially mechanochemistry. Mechanochemistry is just making masala at home. We take all our spices together, we mix it in a mortar pestle, and we get the concoction and we put it into our curry or something. Essentially, this is a mechanized version of exactly that. You take the metal ion powder, you take the organic ligand powder, you mix it together. They call it as the extrusion method. They just have a screw. So you apply mechanical forces, and at the end of this, the tube, you end up getting MOF particles. So they demonstrated this idea in a lab scale, but this has now translated into something like this. So Sigma Aldrich or Merck is one of the biggest chemical companies in the market. And if you go to their website, you search for ZIF8, which is a MOF, or you search for F300, which is another MOF, you get these materials on the market. So you can just basically sit in your office, order these materials online, and you get it delivered to your place. So this is the kind of the power of translational research, that you do basic fundamental research in the labs, and it can actually have some possibilities in a few years' time. The other example that I wanted to highlight is the application. So you might be thinking, oh, these materials are so great, so they would be everywhere. Well, they're not there yet, but there are some signs that they might get there somewhere. So for those who might be interested, there's a QR code here for to scan. This is from a company in Canada, which is called as Swante. What essentially they're doing is cement factories are actually the biggest contributors of CO2 pollution among all the industries. So what they're saying is at the exhaust of the cement factory, you make a membrane of the MOF. The MOF can absorb CO2, and you can just concentrate the CO2 molecules and then geothermally bury it down. So the second part is something that I'm not going to focus on because I'm not talking about that, but I'm talking about the MOF part. So in the exhaust of the flue gas, which is the one that comes from a cement industry, has got a lot of concentration of CO2 and nitrogen. And you can actually design a MOF in such a way that it will only absorb CO2 and it will kind of not interact with nitrogen. So if you have a specific structure that can capture CO2, you can concentrate all the CO2 molecules, and then by a subsequent process, you can release all the molecules and take the same membrane for a second cycle. So this is what this company is trying to do at the moment. They're doing it on a pilot scale. So we're awaiting the results or the performance, what they get out of it. But the connection is from the previous slide. I showed that chemical companies are manufacturing MOFs. So BASF is another company that manufactures MOFs on a commercial scale. So they have tied up with BASF to produce MOFs in kilograms and ton scales. And they're actually using these materials for their applications. The CEO of that company actually had a press conference earlier in this year where he made this public announcement saying that they want to launch a gigafactory. Typically, if we apply catalytic materials that happen in the lab scale, it's really hard to integrate them into textiles or some form of membranes. But with MOFs, we can actually fill that gap. We can actually use these powders to integrate it and then use it for some kind of applications like this. The next example that I wanted to show is Yeah, thank you. The next example that I want to show is we all are living in the age of AI now, right? So MOFs can't really miss this. So in 2021, there is now standard practice in the community that all the data that we produce or have in the labs, that has to be digitalized. So whatever data we are producing in the labs is now into a single format, which is called as this AIF file. This is for gas adsorption, but any gas adsorption experiment that we do in the lab has to be recorded as an AIF file, and this is collected globally. And the implications of it is a paper earlier this year, is, for example, you have to capture CO2 at a concentration of 400 ppm. Let's say this is the target. You just put your target, you let GPT run itself, and you get the specific MOF that can do this. So once you have this information that is stored in you're kind of training the model in that way, you get the output very quickly. So you don't have to spend a lot of hours going through papers and trying to find out which works best. You can actually start using the power of GPT and convert all of this data and hit your target very quickly. So this is where AI is now coming into its own in the field of MOFs. So my final segment is going to be about the names of people who are working with MOFs. And again, the community is growing. It keeps growing every year. So there's a researcher in Germany who actually thought he wanted to collaborate with someone, and then he spent a week finding out people. So he said that this is not something I want to do again. So what he did is essentially create a map, a MOF map of the world. So each pin on that essentially represents a group that works in this area. And there's a QR code again if you want to have a look for yourself. This is a Google Maps image. He created his own. But what I wanted to also highlight is there's an Indian map of MOF researchers. So these are some of the groups that are working with MOFs in India. And as you can see, there are different groups in different states now who are working in MOFs. So I worked with Professor Sujit Ghosh in IISER Pune, but there are people in Kolkata, there are people in Bangalore, there are people in Indore, and there are lots of others. I just highlighted some of them who have got this orange dot over here. So orange dot means that they have a website. We can go to that website and then look up for it. A blue dot essentially means that they are there, but there's no further information. You have to contact them, right? And you can see at the bottom corner, there's Chennai is there. So there's some groups in IIT Chennai, which I'm working, and there's also a group in CSIR. There are also some groups working in neighboring parts of Chennai, which have a pin over there. So you can always look up for more information there. I will end my presentation with one final thing. So Professor Michael Zoratko is one of the pioneers. He didn't win the Nobel Prize, but he's a pioneer in his own sense. He started working in the 1990s, but his research was more kind of looking into the fundamental aspects of how this bonding happens. So he's not kind of regarded as the father of this field, but he's kind of one of the key figures in this field. So the press went to him the day this Nobel Prize was announced, and they asked him, "What is your first reaction?" So he said, "This is sort of the end of the beginning." I'll I'll pause for a second and just read this again. This is not what you usually hear. Usually you hear this is the beginning of the end. What he says is this is the end of the beginning. So what he's trying to mean over here, that the research on MOFs is now finished its childhood. It's now into its teenage and beyond. So this field is now only going to grow from here. So he says that all the immaturity that it had in this field is now done with this Nobel Prize. Now there would be industry people interested in this area. Now there would be more people interested in this area who will fix all the loose ends, and this field will grow in a much better manner. This is what is kind of his statement was, the first reaction to the Nobel Prize. So with this, I would like to thank you again for giving me this chance to present in front of you. And I will finish this with this slide, which again the nobelprize.org had, where they picked up 6 MOFs out of the 1 lakh crystal structures, and they chose these MOFs for specific reasons. So the CO2 example that I showed, where the company Swante is working, which is this one in the middle part of the bottom panel, which is CALF20. The one that I showed for the nerve gases is in the bottom right corner. The one in the water harvesting one is the first one on the top right, top left. And the one which is the one on the sigma is on the bottom right, which is Zephyr. So there are all of these MOFs are kind of very, very useful, and you might hear or see more of them pretty soon. So with that, thank you to all of you.
Thank you.
Thank you Amit, for fantastic. Yeah, we have session for that. Yes, we wanted to complete some of the formalities. One is the library would like to give their contribution.
Thank you.
To this. Okay, okay. I may not be there. Thank you.
Okay, thank you.
Just another 5 minutes we'll take for one more thing. We announce. It's a competition. There was something. People who are Start one. Start 40 predictions. And there is some price distribution for that. I request Professor K. Viswanathan. IISER Mohali. IISER Mohali. And before that, he was an IGCAR. He was a chemistry. So he has been very helpful to all of us in finding the speakers, including today's speaker. And we would now request Viswanathan to join, mention few words, and then we'll finish that.
I just hold it. I won't talk much because I think we need the people questions. I would like to congratulate Aamod for this wonderful presentation. I think this is probably one of the best presentations I've seen in a long time, and I can see a wonderful teacher in Aamod. So with that, very cheerful, yeah, and I think he brought down the concepts. He explained it so well, and in spite of it being so technical, he made it so acceptable to people. So thanks a lot, Aamod. I think a wonderful presentation, really. Yeah, great presentation. Yeah, I think we'll get on with the thing and.
I think that's almost. You want to read?
Think I will.
So we had a contest at the Nobel Prize prediction contest was conducted for physiology, physics, and we didn't get any nomination for physiology. So physics and chemistry we got. Winners are there. So first we go with physics. So winner is Mohammed Aamod. He is from Indian Institute of Space Science and Technology.
Okay, there are two books. So there's a book and some cash. Okay, please.
Hold it.
This is from Indian Institute of Space Science and Rwanda. You come all the way. I was there. We have met. Yes, I did see. Yes. Okay, thank you very much. Next one.
And for physics was he adopted me. So he's E. Majusri from Trichy, Singalashmi Ramasamy College. He informed yes. Now we go to chemistry. Chemistry, the winner is Mr. Ravi Krishnan V. of Hindustan Institute of Technology.
Very nice. The cash price.
Hold this. Oh, no, take out the certificate.
So, what you are doing is that in the Hindustan Institute of Technology. Yes. This doctor is Devi Meenakshi. She is from Sensory College of Arts and Science. She's from chemistry department. She is the speaker for 22nd of this month. We have arranged the same topic. Okay, so she's going to. She has not come today. Since we have also decided to honor who has predicted more near to the topic and the scientist. So we have decided to give installation prices as well as special mention prices. So I will read one by one. Who is present, please come back. Miss Priti Kumari. No, she has not come. I have contacted. She is from Chhattisgarh. She studied in Coimbatore, some product. That time she has is contact with the Tamil Nadu Science Forum. Now she is employed there.
I wonder if, I hope she's online to see this.
Yeah, I sent the YouTube link also. Yeah, today morning. I mean, sometime back I was it. Next is Krishna Leola BCA College. Please come. So, certificate and one book also will be there. We'll be dispatching. Okay, with John Brackens. Next is PRMB. Please come. That's a book also. Next consolation prize is Mohammed Sabir Y, University of Madras. Good job. Next is Miss Maheshwari Kumar, Swami Dayananda College of Arts and Science. Next is Priya B. It's a book also. Yeah. The consolation prize and the special mention prize and also on chemistry will be discussed to you. Next is special mention prize to Sushil C. ABS College of Arts and Science, Salem. Next is Anandi C. Sri Aravindo Matriculation Higher Secondary School. Good job. Next is Mr. Job Singh of Jain deemed to be University. The contacted him, he is not attending today. He was with IIT Madras and now doing PhD. So that's all. Thank you for the training.
Just congratulate all the people who got prizes here. It's a the I think it's a very good exercise trying to figure out who the Nobel Prize winners are going to be, because I think there's a lot to be learned. And as Aamod said, more than the work, I think if you go through their history and the way they discover things, I think that's a great lesson, because most of these people are thinking far ahead of their times, and their ideas and papers usually get rejected to begin with. As he said, their grant application gets rejected because it's no use. I have also seen papers of Nobel laureates being rejected because there is no novelty in it, and then they end up getting the Nobel Prize. And one thing that all these people have done is, they have stuck with their ideas even though they were rejected. For example, the best example I can think of is Dan Shechtman, the author of the idea of quasi-crystals, when he first came up and said that crystals can have five-fold symmetry. We usually think of crystals having four-fold symmetry or six-fold symmetry because they can fill up space, but five-fold symmetry cannot fill up space. So we didn't think of that. But Dan Shechtman said you can have crystals, and he called it as quasi-crystals. He was ridiculed. There was strong objection to his ideas, but he stuck with it, and eventually he got the Nobel Prize in 2011 for that very revolutionary idea that he thought of. It's a good idea to get engaged in this whole idea of who the Nobel Prize winners are going to be, and try to figure out the way they discovered and so on. Their ideas usually start off with being ridiculed, and then there's a hostile or a sort of a skeptical acceptance, and then there is partial acceptance, and then there is celebration. Yeah, and then there is glory. So this is a profile of all these people, and it's very inspiring to go through all that. I don't know how many of you really read that this year's Nobel Prize in Biology, for Physiology and Medicine, I think Mary Bronkow. I think many of us here would have a far better CV than hers. She has 34 publications at the age of 65, but she has a Nobel Prize. We don't, and that's a big difference. So the point is, don't get caught up in how many papers I have and how many citations I have. I think it's more important to see the ideas that you're working with and just enjoying. Thank you.
Okay. Now we will have a last session, which is question answer session. So just raise your hand, whoever wants to ask him, and then we'll go through each one of them to the extent first. Okay. Now, it's not working.
Did I turn it on? Oh, yeah.
Yes, thank you, Doctor. That was a wonderful presentation. I came with some unknown things. I'm going to be sitting there to assist my wife. It was a revelation. IIT side, and their selection process is excellent. So the presentation gave me a couple of ideas. I'm an engineer. I was IIT Delhi graduate. So Delhi is suffering a lot. So we can create a mask so that people can live, and people are getting sick. My colleagues and friends are getting sick there, and even healthy people are getting sick. So we need to create a mask for the Delhi people. And since the Swante is using in a chimney, that is wonderful. So I thought of we can have all our vehicles so that there is no pollution. There is no pollution certificate, BS6, BS5, all will become BS actually. So all vehicles can run indefinitely. So thank you. So how is that? Is it even possible? Those kind of things. Yeah, that's possible.
Sure. Yeah. Thank you for that. Thank you for that. So the one key difference between a flue gas exhaust and the pollution in Delhi is the flue gas exhaust, we actually end up getting concentrated CO2. So the flue gas is more than 70 or 80% CO2. But in Delhi, the pollution might be like 400 ppm or something. That is way lower. So a lot of competing gases with that. So to design a material that selectively captures CO2 from there or some particulate matter, That's slightly tricky at the moment to identify it from a range of mixtures. But getting it from the exhaust, maybe a fuel exhaust, that's actually easy to do. And I think the only yes, carbon monoxide. So that is slightly easier to do. But to get it on a wider scale, the only constraint is the amount of gas that we have. So we have got like, let's say 400 ppm of CO2 in this room at the moment. That would be hard to capture. But if we can concentrate CO2 somewhere or at the point of exhaust, that is slightly easier to capture. So they are targeting that industry because cement industries are the one that produce the most carbon footprint. So they want to trap it there, because then that can automatically reduce a lot of things. But in Delhi, I think that problem is also solvable. It probably needs some time.
Just one subsequent problem, the question to him. It's true that this type of solutions may exist here. But that itself will lead to any kind of environmental problem.
Right.
That here.
Right. So, like my research group is working on sustainable materials. So what I'm going to try and do is use biomass waste or things like that as the building units for creating MOF materials, because organic chemistry is rich in by sense. So we can actually do synthesis based on those precursors, and those can be easily recyclable. So it can be like biodegradable materials. Even if the material is not functioning well, we can just put it into the soil and it can decompose in itself. So the choice of the building units then matters in terms of what we are looking at. And in my group, we are going to kind of look at more sustainable building units. So in principle, that is possible. As of now, no. As of now, the things that are in the market, they still are based on the old idea that we want to first use it for an application, but not look at the sustainability. But that's something that consciously is working around in the field. So you might see a solution soon, maybe.
A couple of questions regarding the data set. Is it open data set?
Yes.
The
AIF is on GitHub and it's perfectly open.
open data set. Okay. And a little bit regarding how these polymers are formed. Is
Right.
it heat energy, or is it going to be any other reaction? And how is it formed? Because you said it can be done at home as well.
Right, right. So, yeah, it depends upon the bonding strength of the coordination. So if it's a weak bonding strength, if it's a nitrogen donor, slightly more technical, if it's a nitrogen donor to a metal ion, that is usually a weak coordination bond. That doesn't need a lot of thermal barriers to be crossed. So that can form at room temperature. But for the stable MOFs, which are more robust, we need some thermal input. So it has to be done at slightly elevated temperatures, or we need some mechanical input, like the one which was mechanochemistry, something like that. Some form of input that is needed.
We have been constantly discussing about the surface area, which actually maps to the volume.
Right.
What about the weight? I mean, if the guest is going to be of a higher dense molecule, what will be the reaction? And
Right. Yeah. So usually the pore windows are up to 2 nanometers, 20 angstrom. So we can't really insert a guest molecule that's bigger than that. So for example, we cannot insert a DNA entire particle inside the pore, but we can go up to like VOCs or something like that. Those are easy to insert inside the MOF structures. But what essentially can happen is you can also use a surface. So recently, when there's slightly going on a tangent here, but recently we kind of worked on one application during COVID, is on a face mask, can we have a coating of MOF? And then that particular MOF, the surface is active, and the surface can be designed in such a way that it interacts with the spike protein of the COVID particles. And essentially, then you're not now moving from a small particle to a much bigger particle. So in principle, that is possible, but getting inside the pore is harder because of the size constraints.
because with the longer organic ligament, you
Yes.
said the volume increases, but the entrance
Entrance is smaller. But then the moment you keep going on and on, the density will go down. And if it goes closer to zero, then the stability of the MOF itself is a problem, because then it becomes too light. Then it might collapse just because of sheer density.
So I understand the utility is around storing particles and extracting
Right.
them. What about other things like creating lighter polymers that are stronger? If I use different metals and
Yes.
organic combinations.
Yes. So instead of MOFs, I would say COFs are slightly better in that regard, because it's now a covalent bond. So that is going to be more stable in terms of a lot of things. So even if we create low dense materials in purely organic form, which are essentially our organic polymers that we know from conventional knowledge, but which have got some periodic porosity. So if we are able to create COFs, we can have the benefits of MOFs in a more stable structure.
How are the guests forced out?
You can either use temperature swing, so you can just heat it up, like for the example of water, when the water gets loaded inside, or you can use some pressure swing, so you can change the pressure of the local environment to remove the gas.
Because when it comes to utility, if it accidentally gets
Right.
forced out, it is a problem.
Right.
So
No, it doesn't. It needs some kind of trigger, so it would either be a pressure swing or a temperature swing. That's the standard way.
Thank you. Thanks.
It's a couple of questions. It looks like most of the time you use the transition metals and have lanthanides and actinides been used in MOFs?
Yes.
And if so, what are the advantages in using them as opposed to transition metals?
So lanthanides would have higher coordination numbers.
Yeah.
That would give more complex architectures and things like that. So people are actually working on RE MOFs, which are rare earth MOFs.
Oh, okay.
They're actually using lanthanides and actinides for it.
Okay.
There is an example of people using uranium as well for radioactive absorption. So you can use them as some material where they can absorb radioactivity in some enclosed environments. That is coming from a group in China at the moment, so it's not much information known about it.
Okay.
But they've reported them off, so they're saying that they might be using it for something. But yeah, it is possible to go down the periodic table as well.
Okay. The other question is, most of spectroscopists and photochemists like doing spectroscopy and photochemistry in confined spaces. And photochemistry actually is quite different.
Right.
Has that been exploited?
It's not been exploited, but a lot of interest is coming in this area.
Okay.
Even I have been contacted by a lot of physics group. They want to kind of learn the pathway of light, how it interacts with the gas molecules in a confined environment. So that is one thing that might be happening soon. These would be transparent to. These are not very transparent because they've got a transition metal, but and the organic ligand also has some absorption properties in terms of light. But if you can get more porous structures, they might have some semi-transparent nature.
So at the outset, thank you so much. It was a great enlightening session. And like when we sit with papers and read, half of it goes over my head. But then this was a great presentation. Thank you so much at the outset. So I just have one question. So when you were talking about zirconium-based MOFs, right? You said that it's far more in the integrity part, and it is a far more stable MOF, right? So basically, zirconium is widely exploited in surgical implants and medical related devices. So when it is clubbed with an MOF metal like zirconium, right? I mean, what is the take there, and how promising it is on the medical field? Do you have any inputs on that?
Yeah. So the reason why zirconium MOFs are so stable is like just going to fundamental chemistry is the zirconium oxygen bond is really strong because zirconium is +4, so it's hard base, and then it reacts with oxygen and it forms a very stable structure. So zirconium oxygen MOFs are very stable. So in terms of application, people have tried to use it in medical imaging, but I'm not an expert on that, so I can't really comment too much on it. But people have tried to do it some form of medical applications. But it's again got to do with the stability because they're quite stable in terms of the pH window. They're stable in buffers. They're also stable in normal conditions, moisture. So the stability aspect is one that is useful. The problem though is because they're so stable, they're not flexible. So we can only use them like for rigid structures. But for some of these applications, it would be nice if we can have some form of flexibility there.
That is the reason I asked, because the porosity in it.
Exactly.
So they club together with the rigid zirconia.
Right,
Is
right.
there any other improvised?
So people are trying to actually do bimetallic MOFs. So they're trying to use zirconium and copper, for example, and they're trying to make the best of both worlds. So Susumu Kitawa is actually proposing a 4G MOF. He's not published it yet, but he's speaking about it in the conferences and things like that. So what he's suggesting is like we can have a core shell structure. We can have a central MOF and we can grow a second MOF around it with the same topology. And the two MOFs can have different functions. So the outer MOFs can do something else. The inner MOFs can do something else. So the application that he proposed in the conference was like, if you can take a gas mixture, the outer MOF can screen the gas molecules. It goes down. and the inside MOF can do catalysis on it, or it can do something else. So that now we have got two MOFs to do different things. So this is what he's proposing as a 4G MOF, but we'll see when it comes out.
I have two questions.
Sure.
Are these conductors, electrical conductors?
They're not strongly electrical conducting because of the organic part. So they're spaced out. So the conducting layer, even if it's there, it is spaced out. But there are conducting MOFs that are coming in, which are two-dimensional, which don't go to the third axis. In that case, they're like 2D sheets, and then they become like graphene.
2D crystalline
Yes, yes,
structure.
yes.
Okay. The next is about you mentioned about the capturing from the cement industry, right? But the main issue is coal thermal plant.
Right.
Can't we use in those things?
Yeah,
there?
yeah, I think we can use it there. The only thing is about the temperature gradients, because these are not stable, unlike zeolites, which can be stable up to 1000 degrees. These are stable only up to 300 or 400 degrees Celsius. So we cannot directly put it at the end of the exhaust, but for cement industries, it's still okay. So they're starting with that, and maybe in some form of modification, it can be coming to coal industries as well.
But that is one of the serious problems.
Absolutely.
which we would be interested. Okay. Okay.
Right.
If you had used the conducting polymer, things that you have as your linkers,
Right.
then you would bring back conducting.
Exactly. So that is how they're making the conducting MOFs. So if you have got a building unit that's conducting in nature, you form 2D layers, and then it's almost like graphite.
Yeah, because we have conducting polymers in although
Yes.
as
So
we haven't even got to conductors yet.
that would be absolutely amazing. Yeah.
Okay. Are there any questions, please? Okay. For the questions, the other section with Aditya.
Before that, let me have a privilege of asking one question. Is there any similar structure or in the nature itself?
So nature hates porosity. So all the naturally found soft materials or even the structures don't have porosity in them. So this is kind of creating, I think this usefulness of useless. And there's a second thing, creation of emptiness. So these structures are with this idea that we create emptiness inside something.
Is something like beehives?
Yeah, it can be there, but like just as a natural structure in our bodies or biologically relevant structures, essentially they don't have porosity in them. So we are kind of going against nature in this case. And to go against nature, we have to form a lot of rules to ensure that we are forming a structure that is rigid.
So basically, it's a invention rather than a discovery.
In some sense, yes.
Go ahead. Okay, last.
So how does MOF react or behave in vacuum spaces?
So in the vacuum that people have gone down to is about 10 to the power -7 millibar or something. In that, they're pretty okay, but I don't know what happens beyond that. So that's something food for thought. Yes.
So they're still integrated and
Yeah, they're pretty okay there. So they're not breaking. I think it depends a lot on that bonding nature. So again, the zirconium MOFs might be stable. Some of those other MOFs might collapse with that lower vacuum.
Okay.
So thank you very much for participating in the prediction contest as well as participating in today's lecture. So thank you very much, Dr. Aamod, for the enlightening lecture, and lot of today's, a lot of solutions are the offering. Many of the problems, even maybe microplastic also maybe will be solved, or some partial solution in the MOF. I don't know. So I hope enough curiosity is generated among you to further, in whatever field you are, you can pursue that. Wishing you all the very best in all your pursuits. Keep coming for the lectures. All the lectures are available in the YouTube also. Today's lecture, including today's lecture. Okay, and we are going to have another lecture on 15th. 8th also one lecture is there on physics, Nobel Prize in Tamil. And the 22nd, as I told you earlier, on chemistry. And we are nearing 100th lecture in somewhere in January it will be held. So it will be a bigger event You can also suggest by email. We will invite your suggestion how it can be done. Okay, and we have a lot of plans. We want to compile all the lectures and present it a half an hour video or something like that. If anybody is interested to do that, you can volunteer yourself. It will be a very nice experience. Thank you all.
Those who want to join the MSF, people are. Take the prize money.
Okay. One more. We omitted to tell that the books and the prize money is sponsored by none other than the IIT Madras only. So, thank you so much.